So welcome to this the concluding part of this gradient and graft copolymer and its composition segment. Here we are going to discuss about the addition polymerization and other approaches which require for the various polymeric systems. So if you recall, in the previous lecture we were discussing about condensation polymerization, and we had a discussion about the nylon 6,6 production. Now here just give you a brief glimpse about and just to refresh your memory about the production of nylon 6. It is usually produced from the intermolecular condensation of caprolactam and polycarbonate, etc. You see, the important of this particular condensation polymerization is that this particular reaction deals with the ring opening polymerization. So it offers a wide spectrum of product profiling, etc. The mechanism and the process offers. So that's why this particular reaction which is at your screen, it offers a very good opportunity for ring opening, because when the ring used to open, then there may be enough active sites to carry out the further polymerization process. So this was all about for the condensation polymerization. Now let us start with the addition polymerization. Now usually if you recall this addition polymerization, previously we discussed, this addition polymerization is a polymerization process usually formed by simply joining of molecules or monomers without the co-generation of any other product. If you recall the condensation polymerization, where there was a generation of byproduct. If you recall the examples which we discussed previously, the water molecule was produced during the course of polymerization reaction as a byproduct, and you need to continuously remove those water molecule to carry out the reaction. But the added benefit to this addition polymerization is that there is no chance of the formation of any kind of allied products, and usually they are simply joining. So sometimes it is referred as other forms. So this polymerization process, they contains sometimes the carbon-carbon double bond, and the repeating unit of polymers may have the same structure as monomer, unlike the condensing polymers. If you recall, in the condensation polymerization, we discussed about the formation of nylon 6,6 or PET, etc. In that case, if you see that the structure of the polymer was entirely different from the monomer. But here you may have an opportunity that addition polymerization, and the polymer may have the similar type of structure with respect to the repeating unit of that particular polymer. So usually, in other words, people may say that the addition polymerization or addition polymer is a polymer usually formed by the chain addition of reaction like this between the monomer, and that contains a double bond or sometimes any active sites which require. So one may create any kind of a vinyl monomer to react with the shape polymer, etc. So there are enough opportunities, there are enough examples like the example of polyethylene, example of formation of polyethylene with respect to the ethylene monomer, etc. Now, I am giving you a couple of examples related to this addition polymerization. The first example related to this is the formation of polyethylene. Now, here you see that this is your ethylene monomer. Now, for efficacy of this particular reaction, you may require some catalyst, and the best catalyst in this category is your Ziegler-Natta catalyst. And this is your polyethylene. Now, you see that this is your ethylene monomer, and this is polyethylene. Now, you see that these units, these are the repeating units, they are joined together to form this polyethylene. Now, this time with the help of a catalyst. So that is the Ziegler not a catalyst in this. Now sometimes you say that if we develop the polypropylene, now here again you see that this is the propylene monomer, and if you perform any kind of a polymerization reaction with the help of say Ziegler-Natta catalyst, then you see that this will form like this, sorry. Now this is the repeating unit. So in some other words you may say that this is the sequential addition of different type of a monomeric unit. If you recall the previous lectures where we discussed about the addition of different type of a monomer to form a long chain or a branched chain, etc. So this is one of the best example of this kind of thing. Now, when we are discussing about the versatility of this particular polymerization process, we cannot overlook the importance of isomerization process, because sometimes its demand, and if you see in the various petroleum refineries, there is a separate isomerization unit for the product improvisation. So, in the chemistry part, it is already well evident that what is the basic concept of isomerization. So usually this is the structural regularity in the polymer, and each molecule or each monomer segment is in a regular configuration. If you see that the previous example where we were having the polyethylene or polypropylene, etc., where each molecule or each polymer system, they are having the regular configuration. Now the benefit of this regular configuration, it gives a definite structure to the polymer molecules. If you recall that we are in the first couple of lectures we discussed that polymer represents in the form of a different chains. So if you wish to predict the behavior of any kind of a polymeric system, then you must know that what is the structure of that particular polymer molecule, like this we have represented. So this particular approach, always we require that we must have the polymers having the regular structure. Now this regularity in the structure of the polymer usually arises due to sometimes optical approach, sometimes the geometric approach, and these are clubbed as optical and geometric isomerization of the main atom or the substituent in different type of a polymeric system. So let's have a look about different type of isomerization, because the product profiling, when we consider the product profiling, this kind of knowledge is quite essential. So the optical isomerization, this the molecules may have the same chemical formula and identical in the molecular weight. If you recall, in the previous lecture we discussed about the importance, some brief importance about the molecular weight, because it is the deciding factor of the various properties of a polymers. Now these molecules may have sometimes same chemical formula, identical, they are identical in molecular weight, and most of the physical and chemical properties are identical, but they differ in the rotation of a polarized light. It is just like that the sugar is available in two forms, dextro and levo form. So this arises due to the different group or substituents on the asymmetric carbon atom in different polymer molecules. So the isomer molecule may have the same number of atoms bond, but they may have a different arrangement. They have non-superimposable mirror image, that is called the enantiomers. If you see that here in this particular photograph or figure, I have given you the mirror image of a particular polymer. Now here you see that although molecular weight is same, all kind of functional group they are same, but still these two polymers are different. So, substance, in other words, you may say that the substance may have the same molecular formula, structural formula, but you can't superimpose them on each other, and that creates the difference in various properties attached to these particular polymeric systems. So, usually depends on the position of pendant group or the hanging group in the polymer, up or lower, that depends on the method of a processing. So, upper or lower part on the plane of the main chain, sometimes dextrorotatory, sometimes levorotatory, etc. So, the name, as the name implies, is that dextrorotatory means turning on the right direction, and levorotatory means turning to the left of the plane polarized light. So, on the basis of this kind of approach or position of the pendant group with respect to asymmetric carbon sites, there are a different type of isomers they exhibit in the polymeric system: isotactic, syndiotactic, atactic, or heterotactic. So, we will have a brief outline of all these different type of isomers. Now, let us have a look about the isotactic isomers. So, this is that when the pendant group, usually sometimes it is referred as the group of atom attached to the backbone or a chain of a long molecule like this here. So, if a pendant group is attached on the same side of a carbon main chain, the molecule there thus obtained is termed as isotactic. It is just like here. Here these are the pendant, they are on the same side of the molecule or the backbone. So, they are termed as isotactic. I am giving you another example of these isotactic isomers. Now, here let us see now here another pendant group, you see. Now, if you see that this is the backbone of the polymer on the plane of, let us assume that it is in the plane of a paper. Now, you see that all the dashed up things are just above the plane of paper, and the bold, whatever we mentioned over here like this and R, they are downside of the plane of paper. So, that means these are the pendant groups like these dash, these are the pendant groups, and they are having the similar, they occupy a similar side of the backbone. So, they are termed as isotactic. So, when the pendant group attached on the alternative site of the carbon main chain, the molecule obtained is referred as syndiotactic. Now, I just am giving you the small figure of this to explain that what is this syndiotactic. Now, here again I am having a polymeric chain, or that is called the backbone chain. Now, here if you see, now here you see that they are these backbones, these pendant groups are on the alternate side, like here H, here you can see H, here H, the R, etc. So, you can see that they occupies the pendant group, they occupy the alternate arrangement in that particular backbone of polymeric system. So, they are termed as syndiotactic. Another, the third part of this particular isomeric system is the atactic isomers. So, when there is no regularity in the attachment of a pendant group on either side of the carbon main chain, maybe sometimes you may refer as the random attachment of the pendant group to the polymeric backbone. So, these molecules thus obtained, they are atactic isomers, or they are lacking in orders, etc. So, you can say that this is the random approach, and there is no fixed approach. And if you recall the previous one, when we were discussing about the isotactic, where everything was aligned to a single side of this one, then we discussed about the syndiotactic, when the pendant groups are in the alternate fashion. Now here the pendant groups are in a random attachment. Now let's have a look about this one. Again, this is our backbone. Now here different sites are available. Now sometimes you may have R over here, sometimes again the R over here, then R, then R, and sometimes here. So you see that this is the random arrangement. This is the random arrangement of the pendant groups across the backbone, and sometimes it is you can say it's a very feasible, and sometimes it is you can say it's very difficult to orient the things. So that's why based on the requirement and based on the engineering approach, you may go for this type of arrangement. Now let us go for the chain growth and step growth aspect of classification of polymerization reaction. So let's have a look about the chain configuration. Now this is quite simple, that the placement of repeating unit into the main chain, they are called the chain configuration. Now in this particular polymerization, the molecules, those who are having the pendant group, let us say R in this case, can be attached in different ways, maybe head to head, maybe head to tail, or maybe tail to tail. So this is the three different type of thing. Now if you see these kind of a classification or different type of a way for approaching the polymeric system, there are different approaches or different ways through which you can generate more and more different type of tailor-made polymeric system. Now here when we discuss about that, the head is usually defined as the end bearing the organic group R. Now this organic group R is again having very important, because it may have active sites or a reactive sites, may have a double bond, etc., to carry out the further configuration in due course of time. Now just I am giving you an example that the chain polymerization of a vinyl molecule with the organic group say R as a side chain. So among all type of attachment, head to tail attachment is usually favored, and usually structure formed is dominating one. Now here you see that by this way you can visualize the thing. Now I am using the vinyl monomer. Now here this is the structure of vinyl monomer, and if you add, this is this become the number of number n is the number of repeating units. This is the repeating unit. Now if I see that we discuss about the head to tail. Now here you see that This is head to tail type of a system. Now if you see if you try to compare with the head to head, we will discuss in C2. Now another example of this the vinyl monomer is carried with the head to head one. Now just see again, come back to the monomer side. This is my monomer. Now if talk about the head to head, that means you see that what is the difference. Now this is head to head. Now if you recall the head to tail, where the configuration was like this. So this was head to tail. Now see the difference here and here. You can clearly visualize that the molecular system is same, molecular weight is same, but the properties of the polymer would be bit different. Now come back to the tail to tail. Now here you see that again the same monomer. This is the vinyl monomer and the arrangement is like this. Now this is the tail to tail. Now if you compare with your head to head, the head to head was CH2, CH, CH, CH2 and CH3. Now this was head to head, and if you compare with the head to tail, you see this is head to tail. Now you see the difference among all three approaches, and you can see that if we go for the any kind of polymer, the polymer may have different properties compared to the other one. Although they are having the same molecular weight, they are having the other things in common, but they may have entirely different properties. So this is just about the chain thing. Now there are certain geometric type of isomerization process or isomers. So for these type of isomerism process, the two carbon-carbon double bonds are usually involved. The different configuration of pendant group on carbon-carbon double bond and their position, usually they are attached in the molecule, gives a different type of a geometric isomeric configuration. It is bit different from the mirror image which we discussed earlier. Now let us have about, there are two type of geometric isomerization, cis configuration and trans configuration. Let us have a look about the cis configuration. Now if the R group, which is our more common group, R group is attached on the same side, that is closed to each other of the carbon-carbon double bond, then they are called the cis configuration. I am giving an example of a cis configuration. That is, you see that this is the repeating unit. Now this is the example of cis configuration. Now here if you recall that the repeating unit of this particular approach, that the carbon-carbon double bond, they are, the R group is attached on the same side of carbon-carbon double bond. Now, if you go for the trans configuration, now if you see that the R group, that is the side chain, is attached on the different side of that particular molecule, that is away from each other, from the carbon-carbon double bond, then the configuration is called as a trans configuration. Now, here you see that this is now this is the repeating unit having trans configuration. Now, here you see that the side groups, they are away from each other, right. Now, if you compare with the cis configuration which we discussed in the previous slide, you see that this is a more clear picture about this one. Now, you see that here the R groups, the position of R group, and here this one is having along the side, and here you are having thus the different side of the things. So, we have discussed about in brief about the isomerization system and other things related to the development of a polymeric system, and these type of things are quite essential while we try to control the polymerization system, how we can control it, because how we can change the molecular weight, how we can have a different type of a polymer with respect to the different the same type of polymeric molecules, etc., same type of a molecular weight, etc. So, it provides you a broad spectrum for the development of any kind of a polymeric product. We have enlisted couple of reference further knowledge or further reading, etc. So, by this way we are summing up this particular lecture. Thank you very much.